Hi, I'm Chen from the University of Texas at Austin, advised by Professor Al Bolvik. And in this video, I will be presenting a progressive architecture for learned fractional downsampling, which is a joint work with Netflix. First, let's review how a video encoding pipeline looks like. Generally, pristine source videos are processed and encoded where these two steps happen on the streaming provider side. Then the bitstream is sent, decoded, and may also be post-processed. The last two blocks happen on the client side before displaying to the viewers. Of course, video quality measured from the source video and playback is also very important. It is one key ingredient to determine the encoding recipe. More precisely, in the adaptive video streaming scenario, the pre-process and post-process blocks are downsampling and upsampling operations, respectively. The reason is because downsampling a video reduces compression artifacts given the same bit rate, but it also introduces more scaling artifacts, such as blurry or jaggies. Streaming companies utilize the trade-off between compression, scaling, bitrate to deliver best video quality at given conditions. In this work, we aim to improve downsampling, which is the bold-face block. Our goal is to improve over the existing baseline, which is length interpolation, by data-driven approaches. Here, we list some design targets that are quite important if you want to make it useful in practice. First, it is desired to be a drop-in solution, meaning that we can easily plug this model into a pipeline without much changes. To achieve this, the model has to be general enough to other components, such as video codecs. Second, the model has to support fractional resize factors. Think about the case of changing 1080p resolution to 720p. This happens every day on the internet. And in fact, the scale factor of this case is 1.5. In addition, we do not have prior knowledge about which upsampler being used on the device end. Therefore, our model needs to be trained in a way that can generalize well to different upsampling algorithms. And of course, we don't want a model that is too computationally expensive. This is a high-level training graph of our CNN model. Basically, we mimic the encoding pipeline shown in the previous slide as close as possible. The source patch is fed into CNN downsampler, resulting in a low-resolution representation. Ideally, there should be a video encoder after this, but since it is not a differentiable component for backpropagation training, we simply remove it during training. So the downscaled patch is then upscaled back to the original resolution, and we minimize the mean square error between the source patch and its reconstruction. For the upscaler shown in this figure, we adopted bicubic interpolation because we found that it can generalize well to different upsampling algorithms, as we will show later. Our model is composed of two subnetworks. Both are doing residual learning. The first subnetwork is called pre-downsampling network. Normally, no resolution changes happen here. It tries to do some pre-coding to compensate the information loss arising from downsampling. We call the second subnetwork as the post-downsampling network, where downsample happens in the first layer of this subnetwork. The main purpose of this subnetwork is to repair the information loss. Actually, this architecture is inspired by the polyphase representation used in multi-rate signal processing. If you compare them, they look quite similar. And this architecture can also be handling non-integer scaling factors easily. You just need to express the fractional factor by L over N, where L and N are both integers. For example, if you want to downscale by 1.5 times, you can upscale by 2 in the first subnetwork and then downsample by 3 in the second subnetwork. Here we visualize the learned residuals. You may have noticed that the learned residuals are mostly located at edges or regions with rich textures. This is not surprising because low frequency components, the flag regions, are less likely to be affected by scaling. It may also be observed that the pre-downscaling subnetwork has relatively more residual values than the post-downsampling subnetwork at 5x. This is hinting that the pre-downsampling subnetwork becomes more important under extreme downsampling. Here is a visualization to get some idea of the difference between different training methodologies. I use a video frame from the honeybee sequence in the UVG dataset. On the right, I show 2 crop patches for better viewing. Here is what happened when you downsample by lengths with a factor of 2 and then upsample it back by using bicubic. The details are blurred out basically. When we replace lengths by our model, which is trained with bicubic upsampler, we got more detailed preserved, which looks better. Interestingly, when our model was trained with bilinear and tested on bicubic, the results looks even sharper than at the first glance. But you might want to be careful about this seemingly good result. It is sharper than the source video. This overshot result is not what we want in video compression because they are also considered as fidelity loss. And we also have some quantitative analysis on this. In this table, we measured the reconstructing quality of a video downsampled by one model and upsampled back by the other. We show PSNR, SIM, and VMAF in each cell. The main message that we want to show here is that when your model is trained with bilinear upsampling and tested on bicubic upsampling, the reconstruction quality is worse than length's baseline due to the over-sharpened result that we saw previously. This is why we end up using bicubic upsampling during our training. And finally, we evaluated downsampling models on an H.264 encoding pipeline with wide ranges of bitrate and quality. We tested the models on 45 source videos collected from CIF.org and some licensed Netflix titles. BD rates of CNN models against the length's baseline were reported in terms of PSNR, SIM, and VMAF. And the other components in the pipeline were the same for each comparison. We tested on both bicubic and bilinear upscaling to understand the generalizability. Now, let's look at some quantitative results. We compared our model with a very recent deep learning-based downsampler called CNN-CR. It was published in TIP of 2019. And it is not applicable to non-integer scale factor, which are 1.5x and 2.5x in this table, because the resolution change is handled by setting the stride parameter of a convolutional layer. On the other hand, our model can handle this issue by combining upsampling and downsampling subnetworks. Performance-wise, these two models were almost identical, where we can see improvements over length's baseline on different scenarios. However, as the scale factor goes up, we started seeing that the proposed progressive architecture performed better than CNN-CR, especially on 4x and 5x. Again, we see improvements over lengths on most of the cases, except one anomaly. As I circled here, we see one case where CNN-CR performed worse than lengths. This may have been that we did not consider video encoding during training. So the model might produce something with slightly better PSNR, but also consumes much more bits. And our progressive model still outperforms Lanxess in this case. You might also be wondering how fast or how slow these CNN models are. We measure the runtime in terms of frame per second on 7 1080p videos on the UGC dataset. We reported the end-to-end runtime, including model loading and color transformation. First, it is obvious to see that Bicubic and Lanxess implemented in FFmpeg achieved real-time performance, which is known and expected. On the other hand, the two CNN models were quite slow. They were around 1 frame per second, even with the speed up from GPU. Another interesting thing is that our model was extremely slow on 1.5 and 2.5x. This is because of the downsample by 2 in the preprocessing network, where the pixels to be processed were doubled. And finally, we are also aware of some limitations of our downsampling model. First, as we've seen in the runtime comparison, the upsampling subnetwork makes the model perform very slow. Imagine that you want to downscale a 4K video by 1.5 times. It will become 8K in the network. This problem can be avoided by a simple building block that we proposed earlier in this year. Secondly, we did not consider video encoding in the end-to-end training due to its non-differentiability. So there is room for improvement on this aspect. And finally, this kind of learned preprocessing techniques may be extended to solving other problems, such as the bending artifact. The benefit of preprocessing is that you don't need to change anything on the device side. And that's it. Thanks for your attention.